Yeah, I think we should.
Okay, great. Okay, let's start. So we're very happy to invite Professor Xiao-Jun Chen from Sichuan University to tell us about battling Minkowski and gravity algebras on Poisson manifold with semi-simple modular symmetry. Thank you, Xiao-Jun.
Okay, thank you for invitation. It's a great pleasure to give a talk. So today the title, as Qingzhan has said, is PV and gravity algebras on Poisson manifold with semi-simple modular symmetry. So this is a joint work with our students, Liu, Yu, and Zheng. So let me start from some background. So in 1997, so inspired from von Neumann algebra theory, Einstein introduced the notion of modular vector for Poisson manifolds. So let's recall his definition. Suppose M is an oriented manifold with Poisson structure, say pi, and a volume form. Then the modular vector of M denoted by nu is a divergence of the Poisson bivector. That is, nu is equal up to a sign is star inverse composed with D and composed with star, where star is the contraction with the volume form. So actually, Weinstein's original definition is more general. So here I only use this definition, which is good for our purpose here. So modular vector is one of the fundamental concepts in Poisson geometry. So in this talk, we studied some of its homological properties. So now you see, let's go over this divergence operator. So first, let's denote delta to be, say, a star inverse composed with D, composed with star. Then we have the following commutative diagram. Here, X dot of M is the space of polyvectors, and omega dot M is the space of different forms. And the vertical, the horizontal is the contraction, and is also the star operator. And the vertical arrow D is a Drum differential. So D is just a composed of these three operators. So now, well, this is a commutative diagram. Now let's look at another diagram. Here you see the horizontal maps are the same as the above one, but you see the vertical arrows are different. So the first one, the left vertical arrow delta is the Poisson co-boundary, which is also the lead derivative of the Poisson bivector. And this one is the Poisson boundary operator. So, well, you see, this second diagram is not commutative in general. So the key point is the volume from here, the omega, the eta, the volume here is in general not a Poisson cycle. So that makes the diagram non-commutative in general. So a theorem obtained by Ping-Xu in 1998 is the following. So suppose M is a Poisson manifold with volume form eta. Then you see we have two statements. The first one is the modular vector nu is a Poisson cocycle. Well, if we rescale the volume from eta by an invertible function, then these two modular vectors differ by a Poisson one co-boundary. No, I should say two co-boundary. Then, oh no, you're right, one co-boundary. That means you see the class that the nu represents is a well-defined is a invariant of the Poisson structure. So it's also say the invariant of the Poisson manifold. So now second statement is eta up to a scalar I just described is a Poisson cycle if and only if nu is 0. Means you see, if nu, the cohomology is 0, then we can scale this volume form so that this nu is 0. So in other words, nu is the homological obstruction to the commutativity of the diagram, the second diagram. So now you see the cohomology class is usually called the modular class of M. If this modular class is 0, then M is called a unimodular. If it's if it's unimodular, then from this diagram, because the horizontal maps are isomorphisms, and then we have the following corollary. So suppose M is a unimodular Poisson A manifold. Then we have the following isomorphism between Poisson cohomology of M and the Poisson homology of M of the degree.
Sorry, may I ask, could you recall what is again Poisson homology?
Oh, Poisson homology. Okay, I'll go over this in a special in another case very soon. So you see, it's no basically take the lead derivative of the volume, the different forms with respect to the Poisson bivector.
Okay.
So now you see, this is the case where M is unimodular. So now, what can we get if M is not unimodular? So now you see, because Poisson homology is defined for the functions on this Poisson manifold. So now let's denote A to be the functions, say smooth functions on M. But you see, the result holds for algebra varieties. So if M is a affine variety, we may take the A to be the defining algebra of this variety. So now let's consider the following twisted Poisson module on A itself, which is denoted by A nu. It's given as follows. So the underlying space of A nu is A itself. And you see the product of X, say in A nu with U. U is in A, is the original one. But you see the bracket of X with U is, is a sum of two terms. The first one is still the usual Poisson, the module structure, Poisson bracket. But you see with extra term, the second term is X dot nu, acting on U. So you see, this is we have this term. So since nu is a Poisson cocycle, and we can check that you see A nu that's defined is a Poisson A module. So it's a new module. So it's called a twisted Poisson. It's twisted Poisson module of A. Twisted Poisson Poisson A module. Yeah. So the Poisson complex of various value in A nu, is exactly the same as before, but no. Is the underlying space of Poisson complex with value in A nu is the same as before as the underlying space. But you see the boundary now changes. It has an extra term which incorporates nu. So you see, if we denote this nu complex by omega dot A with d nu, then you see this d nu is given by the following. Oh, I forgot to say. You see, this d is the original Poisson boundary. I said I will explain, but I didn't here. So you see d nu here, this partial is the lead derivative of this different form with respect to a Poisson bivector. We can also define by using Cartan's formula. You can say this is I composed with d plus d composed with I, where I is the contraction. So this is the second term. You see, this is the second this twisted term. The second line is the twisted term. So you see, With this,
Can you say it again? What is the homology? So now without this mu, just this partial gives you homology.
yeah, homology called the Poisson homology of A. So this partial is you can you see I didn't write here.
What do I do? I do derivative of what?
It's just the lead derivative of this four different form with respect to this bivector pi.
But isn't it just I pi d minus di pi?
Yes.
I mean contraction.
Yes.
So contraction with pi compose. So I pi. That be the contraction I pi d minus di pi, right? Or is it plus?
Right, minus, right, not plus. Sorry, yeah, minus. So,
sorry, possibly stupid question. Why does it actually square to 0?
Because if you use this I pi composed with d minus d composed with I pi, and if you square it, you see first there are several zeros, and because this is a pi is a Poisson bivector, so pi is 0, you will get 0.
Okay.
Yeah, it's just a direct check.
Okay, thank you.
No problem. So now you see, then we have, you see, the following diagram. You see, now you see with this extra term, so we have the following diagram, which is commutative. Means the original one, you see the original diagram we introduced here. You see there is a discrepancy. We have to, the difference is exactly given by this the second line. So with if we add this term to this boundary, you see then you see this is a commutative diagram. So now because again because the horizontal map is now isomorphism, we get the following twisted Poincare duality. Suppose A is a Poisson algebra. If A admits a volume form, say eta, that is, there exists an M form eta such that the contraction is an isomorphism. Then we have the following twisted Poincare duality, which is between the Poisson cohomology of A and the twisted Poisson homology of A with value in A nu. So here I repeat the definition of A nu, which is the A bimodule whose underlying space is A with this new Poisson module structure. So now you see this HP is the Poisson homology, and HP dot lower dot and HP upper dot is Poisson cohomology. So is it clear so far? So as a corollary, you see, I just apply this to manifold cases. Suppose M is oriented Poisson N manifold, or say an n-dimensional Poisson-Calabi-Yau affine variety. So in both cases, the manifold or the variety has a volume form. So let A be the smooth, or say in algebra section, the algebra functions on M, then there is a twisted Poincare duality. Which is, well, let's say between cohomology of
Poisson affine variety. What is a Poisson Calabi-Yau affine variety?
So now you see this is in algebraic setting. Suppose I have a affine variety, then you see we can consider the functions on this affine variety, right? And the Calabi-Yau, I mean, by Calabi-Yau, I mean it has a volume form. And you see by Poisson Calabi-Yau affine variety, I mean, so this variety has a algebraic Poisson structure. So, but you see again, the volume form of this affine variety may not necessarily to be Poisson cycle. So that's what I mean
Okay.
by Poisson-Calabi Poisson variety. So we have the following twisted Poincare duality, actually between the functions on this M and the Poisson homology of A with this twisted module structure. Here, nu is the modular vector of M. So now you see, let me give a remark. If M is unimodular, which means, this modular vector is 0, then this is a theorem of Xu. So basically, this result generalizes the result of Xu to not necessarily unimodular case. And there are some previous works on this Poincare duality. You see, this is probably given in 2002 by Launois Richard for quadratic Poisson algebras. I will say some words about this later. So also by Zhu from Shanghai and Lu Wanwu from Fudan University for Poisson polynomials. So they only consider Poisson polynomials, but for general manifolds, I think this is the most general one. So now,
can I, Xiao-Jun, can I ask you this? This is just it's a commutative diagram on the cochain level, right?
Yes.
It just follows from a commutative diagram. Am I right?
No. You see, this is a commutative diagram, right? But the delta is boundary. So if you see, because this is a now commutative diagram which respects boundary, so you can take homology on both sides. So still, it's an isomorphism, right? I just didn't write. Actually, the vertical arrow, it has a long. You see, it's a complex. I just omitted the rest of terms because this delta squared is 0, and this d nu squared is also 0, right? So you see both the left vertical line and the right vertical line are complexes, not just two terms. And if you take homology, you get the isomorphism, right? Because the horizontal one is always isomorphism of vector spaces.
Right. Thank you. Yeah.
So anyway, actually, this is you see, because you see this this is actually a topological one. It's isomorphism of Poisson manifolds, this Poincare duality, because everything only depends on this Poisson structure. Actually, it does not depend on this volume form. So this is an invariant of the manifold itself. So now let's go. You see, I want to say some words about the applications of this isomorphism. So now first, let's go back to the unimodular Poisson algebra case. So which was discussed by Ping Xu in the same paper in his 1998 paper published in CMP. So let's recall that we have the following two commutative diagrams because we assume the manifold is unimodular. Then you see it's easier to check that this Poisson complex with Poisson boundary and Drum differential forms a mixed chain complex. You see, means D and D, this delta and D commute. You see D plus delta plus D square is 0, and it's co-homology on the cochain level. This delta with this big delta from the mixed cochain complex, because you see now it forms a mixed complex. You see we can define this D on homology level, or say this delta on the homology level. So we have the following result obtained by Xu. So suppose M is a unimodular Poisson manifold. Then you see the Poisson cohomology of, I should say M, with the delta, you see, is a BV algebra. So the delta is called the BV operator. You see, which generates the Xiao-Jun bracket. I will explain this in the next page. But let's just recall that this delta is exactly the delta we introduced at the beginning. So here, this is the delta. So now, what is a BV algebra? So a BV algebra is a graded commutative algebra with with an operator delta, where delta squared is 0, and you see they say this is called the deviation from being a derivation. Is derivation. What do I mean by this? You see, suppose now if I consider delta of A dot B minus delta A dot B minus up to a sign A dot delta B. Well, if this term is 0, means delta satisfies Leibniz rule. But you see, in general, this is not necessary to be the case. So if we define bracket to be the, say, deviation from being a derivation, then it's a derivation for both arguments, both for A and B. So here in this theorem, in the theorem Xu, actually this bracket is exactly the Xiao-Jun bracket. So that's why I say delta is a BV operator which generates the Xiao-Jun bracket. So you can say that because the Xiao-Jun bracket comes from delta. So this is what Ping Xu said, it's a generator of this bracket. Actually, you see, in 1990s, BV algebras were studied by a lot of people. So it arises from string field theory and have recently been widely studied by both physicists and mathematicians. So in particular, in 1992, Getzler, in a series of papers, showed that a genus 0 two-dimensional topological conformal field theory is nothing but a BV algebra. Means, you see, you may view a BV algebra as a genus 0 two-dimensional TCFT. So this is an equivalence. So while the equivalent version is a gravity algebra. So equivalent 2D TCFT is a gravity algebra. So because this is a relatively new concept, let's go over its definition. So suppose V is a graded vector space, say over K, a field. So a gravity algebra structure on V consists of a sequence of graded skew symmetric operators called the higher brackets, such that it's the following called higher Jacobi identity. So it means if there is no y1 to ym here, then you get 0. Otherwise, it is given by this formula. So this is called gravity algebra. So actually, you see, this is related to the BV algebra because, for example, here I said the gravity algebra is an equivalent version. So there is always a relationship between, say, homology, ordinary homology with a group action and the equivalent homology. So it's the same here. So now let's give a construction of the gravity algebra from the BV algebra. So suppose C, B, say big B is a mixed complex and denoted by CC negative dot, the negative secret complex of C dot. Then we have the short exact sequence, which is easy to see. This is a short exact sequence. And then where I is given by this embedding, because it's embedded into this space. And then pi is a projection. So then you see it gives a long exact sequence from this short exact sequence from the negative cyclic homology, and this is a negative cyclic homology and Hochschild homology. Here, Hochschild homology is the B homology of this complex C. So it comes from cyclic homology theory. Then you see we have the following result. So you see for unimodular, in our case, you see, suppose I have a unimodular Poisson manifold, then this is a mixed complex. And then we can consider the associated negative cyclic homology, which is denoted by HC negative dot of M. Then you see with previous result, you see if we define a graded skew symmetric operator like this, so it maps x1 to xn to be this pi of x1, pi of x2, and so on, and then multiply them and then apply beta to it. So now let's go to here. So you see xi is in this negative cyclic homology. You see, apply pi to it, you get the elements in Hochschild. And then you see, if you multiply them and then apply beta again, you get you go back to the negative cyclic homology. So you see, this is a this is a well-defined map. And then you see, it's extremely easy. Just to use definition, we'll see that this is a gravity algebra. You see, with a bracket defined like this, it gives a gravity algebra. Here you see we used the product on this space. This is the BV this algebra. So it comes from BV algebra, which is in general non-trivial because if you apply delta to it, you will get the Xiao-Jun bracket, which is in general non-trivial at all. So you see this gravity algebra is not trivial either. So in other words, we get genus zero equivalent two-dimensional TCFT. And as I said, since BV algebra is non-trivial, so the gravity algebra is non-trivial too. So the previous result does not hold for general Poisson manifolds because you see it's such a manifold may not necessarily to be unimodular because this complex now, you see, as we for non-unimodular Poisson manifolds, it's better to consider this twisted complex. You see, this D nu, this delta nu, this D is not commutative.
Xiao-Jun, where is the equivalency? So you are saying that gravity algebra is the equivalent version. So where is the equivalency?
You see, it comes from, you see, if you study the cyclic homology and Hochschild homology, right? Usually, the Hochschild homology computes the space of the homology of the loop space. And the equivalent one, you see the negative cyclic homology computes the equivalent homology of loop space. I mean, so now this is parallel to that. Is it clear now?
Is parallel to, okay, so because your gravity algebra is HC minus or
yes. Yeah. So you see, if you view C as the complex of the loop space, then this computes the equivalent homology of the loop space, and this computes the equivalent homology of the manifold of the not the equivalent, the ordinary homology of the loop space.
Okay. Okay.
So now you see what I said here. Is just say simply Poisson analog of that. Is it clear now?
So the other one was the Poisson algebra and Poisson homology and is the gravity.
Yeah.
Okay.
Mhm.
Okay, thanks.
So I will give more details about that later. So now you see, let's go to this non-unimodular case. And this complex is not a mixed complex because there is an extra term comes from the twisted module, right? But we have the following identity. So the d nu composed with the Durham differential plus the Durham differential composed with d nu is equal to this nu tilde, where nu tilde is given by the following formula. So you see, it's given by the formula like this. So you see, so this is in general not zero because this nu is this modular vector. It's not necessary to be zero, as I said. So this leads us to consider a special kind of modular vectors, which are those semi-simple or say diagonalizable ones. So this is also important concept in Poisson geometry. So now suppose nu now is semi-simple, which means diagonalizable. Then denote by omega dot lambda of A d nu to be the eigenspace of nu tilde, this nu tilde corresponding to eigenvalue lambda. Then you see this previous equality, I mean this one gives us the following. You see, if you restrict to this eigenspace, you see you will get lambda times the identity, right? So this is easy. And then you see from this identity, we get the following two statements. So it says, suppose M is a Poisson manifold with semi-simple modular vector. Then you see the eigenspace of omega dot A with zero eigenvalue denoted by omega dot 0 A. Together with...
Sorry, could you repeat?
Yes.
What does it mean semi-simple? Does it mean that in some way you have a direct decomposition into...
Yes.
Thank you.
So now you see, if we consider this subspace, you see, consider the eigenspace of with respect to eigenvalue 0. Then you see d nu, this partial nu and d from a mixed complex, because from the above identity, you see now lambda is 0, right? And then you see also from here, if lambda is non-zero, then this complex is acyclic, which means you see this zero vector space together with this twisted differential is homotopy equivalent to the total complex.
Sorry, may I get back again to this semi-simplicity? What does it mean geometrically?
So I don't know.
Are there some examples of such semi-simple cases?
Yes, there are a lot. You see, for example, let's I will discuss later. For example, I give example. For example, this pi is called a quadratic, right? So this is also studied a lot by symplectic Poisson geometers. This is suppose I have a quadratic Poisson structure. If this I1, if this coefficient is like this, suppose I1 is not equal to J1 and I2 is not equal to J2, or say suppose if you sum over this, if this I1 and I2 is equal to J1 and J2, then you can check that this quadratic Poisson structure is diagonalizable. It's like a Durham differential, right? So if you write it, it becomes something like a sigma of xi times partial over partial xi. Is it clear now?
Yeah, it's fine. Yeah. So we'll see again when you consider examples.
Yes. So now you see, yeah, homotopy. So now you see with the same argument as the Xu, because now we can consider the subcomplexes. You see, this subcomplex computes the whole original Poisson homology, right? So with the same argument as Xu, we get the following. Suppose M is a Poisson manifold with semi-simple modular vector, then the Poisson Coulomb homology has a BV operator, a BV algebra structure where this BV operator generates the Xiao-Jun Chen bracket, and the negative sigma homology has a gravity algebra structure. So the argument is parallel to Xu's. Also, it's completely analogous to Xu's result. Here, by negative sigma homology, I mean the negative sigma homology of this complex, and again, it's non-trivial. So I want to say that recently we learned that Wang, Wu, Zhou, and Zhu from Fudan University and the East China Normal University have also got the first statement in an unpublished preprint. So now here, what I discussed so far is about the Poisson algebras. Actually, there is another version of Poisson algebras, which is called Frobenius Poisson algebras. So let me start from an example. Now suppose A' is the exterior algebra generated by n elements. We may view it as the graded symmetric algebra generated by, say, xc1 to xcn with a grading of each xci to be -1. Then there is a degree n, A by A' modular isomorphism from this algebra itself to its dual space. Here, the A anti-Schreck is its linear dual by the following formula. So it's just like a contraction, So now it's direct to see that again this eta Schreck is this is non-degenerate, and hence gives a symmetric Frobenius structure on it. So we also we write the eta Schreck to be the form Xc1 star to Xcn star. And call it the volume form of a Schreck. So now you see the point is the definition of Poisson cohomology and homology remain valid for graded Poisson algebras. So here I view the exterior algebra as actually as functions on the supermanifold, say R0n. So this is a finite dimensional algebra. And you see, suppose now this supermanifold has a Poisson structure, which is graded. Then you see it forms a Frobenius Poisson algebra. Well, here by Frobenius Poisson algebra, I mean this algebra is Frobenius, which means it has a non-degenerate pairing, but it not necessarily to be compatible with the Poisson structure. So this is a notion introduced by Zhu, Wang, Oysterjan, and Zhang about more than 10 years ago. Then you see the above isomorphism induces a map, which is from the polyvectors of A anti-Schreck with value in itself to the polyvectors of A anti-Schreck with value in its dual, which is given by the formula like this. You see, well, you see from here, you see we know that this x dot with value in A itself, A Schreck itself, and x dot with value in A anti-Schreck are Poisson co-chain complexes of A anti-Schreck, Schreck with value on here. This is explanation. So it's with value in these two modules. So now again, this contraction gives the following diagram, which in general does not commute, since this Poisson this volume form is not a Poisson cocycle. Means the isomorphism between A Shrek and A anti-Shrek is not Poisson. So now you see, to adjust this discrepancy, you see we apply the same technique as before. So consider the following. So the divergence, like before, you see we consider the following commutative diagram. Here, this D star is the dual Durham differential, because here we may view this polyvector with value is due to be by direct check to be the linear dual of the Durham complex. You see, the right-hand side is a linear dual of the Durham complex. So you see, we can apply the dual of Durham differential to it. So we get the following commutative diagram. And let the new Shrek to be the divergence of pi again. So we still call it the modular vector. Then you see with this, we get a new Poisson structure on this anti-Shrek. As before, means you see we get that we have to twist with this modular vector action, and denote this new Poisson say co-boundary by delta nu. Then we have the following commutative diagram. You see this horizontal one is always the isomorphism. Yes.
There's a question from an audience asking you whether this eta should whether this eta should is very tiny volume form.
Yes, what?
Is a very tiny volume form.
I don't know. Probably. You see, I just probably, but I don't know this this notion. Here it's just the linear dual of A itself.
Okay.
Excuse me. Yeah, I'm sorry to interrupt. Yeah. It's just that on this A Shriek that you define as these are functions, generated by these odd generators. So this algebra. So it's functions of the purely odd supermanifold, and there is a notion of volume form on the supermanifold that's called the Berezinian. So in the purely odd case, it transforms by multiplying by the inverse of the Jacobian matrix transformation. It's kind of like a multi-vector field instead of a top degree volume form. So it went kind of too fast, so I didn't have time to absorb it. So I'm asking, so is your eta Shriek a volume form in this sense?
I think probably yes, because you see, I said that you see this volume form is like this, right? C1 star 2. This is exactly in my mind. It is exactly partial over partial x1 wedge till partial over partial xn. So I will say a little more about it. So in this sense, I think you are right.
Okay, so if these Xi stars transform as DD Xis, then I think the answer is yes.
Yeah. So I will talk more about this later.
Thank you for interrupting.
No problem. So now you see again we have this commutative diagram. We just need to twist the differential on the right hand side by this vector, this modular vector. We have suppose A Shrek is a Frobenius Poisson algebra, and the new Shrek to be the corresponding modular vector. Then we have the say Poisson cohomology of A Shrek with the Poisson cohomology with of A Shrek with value in A anti-Shrek, but twisted with this modular vector. So this holds for any Poisson algebras, not necessarily to be unimodular. So you see, we again, now we may consider those modular vectors which are semi-simple. Then, like before, we have the following result. Suppose A is a Frobenius algebra with semi-simple modular vector. Then you see its cohomology has a BB algebra structure, where again delta generates the Xiao-Jun Chen bracket, and then the cyclic Poisson cohomology has a gravity algebra structure, where the bracket comes from the BB algebra. So now you see, as I just said, we can compare this Poisson homology and the cohomology with those coming from associative algebras, where we consider the Hochschild homology and the cohomology. So you see, now let's go to make this comparison more precise. So here now, the previous obtained structures arising from Poisson algebras are highly related to the ones from associative algebras. Now, for simplicity, we assume A is just the polynomial algebra. So now recall from, well, this gives a definition of deformation quantization of A. So it gives a new product called the star product on, say, on this A tensor with this formal power series, such that the first non-commutative is given by this Poisson bracket. So in 1997, Kontsevich gave an explicit construction of deformation quantization of A for any Poisson structure. So now you see, what I want to say is, well, if you consider the polynomial algebras, so the deformation quantization, you see, has the following property. It is Artin-Scherter algebra in the following sense. Suppose I have algebra A. We say it is called Artin-Scherter regular algebra of dimension n, if it has global dimension n over K, such that the exterior x of Ka over A is equal to A if I equals n and 0 otherwise. So any AS regular algebra admits a natural automorphism. So you see, actually, you may view, you get from here, either A and K are left modules or right modules. So you see, but these two left and right modules are different. So they are not compatible. So there is a difference between them. So this difference is described by the automorphism of A, which is called the Nakayama automorphism of this Artin-Scherter algebra. Then you see a result of Dorgoshev proved in 2005 or 2008 says the following: suppose I have a Poisson algebra, say like polynomials, then let the AH bar to be Kontsevich deformation quantization. Then you see this deformation quantization is the Artin-Scherter algebra. And moreover than that, the deformation quantization of nu is the Nakayama automorphism of this Artin-Scherter algebra. So this deformation quantization relates the modular vector of this Poisson algebra with the automorphism, the Nakayama automorphism of its deformation quantization. So more precisely, this Nakayama automorphism is exp of nu h bar. Here roughly, because I didn't say much about this Kontsevich's tangent map. Basically, you see, you have to map this nu by Kontsevich tangent map to the Hochschild complex, or Hochschild-Kuchian complex. But this is basically well, you see, just look at the formula. It's basic. It's roughly true. So as a corollary, we say that if nu is semi-simple, then so is sigma. So as a result, we have the following. Later. So Kontsevich and Schochit showed that there are isomorphisms between the Poisson cohomology and the Hochschild cohomology of its deformation quantization via the so-called tangent map I just mentioned. But in our case, because we want to study the Poincare duality between this cohomology and homology, so it is more interesting to consider the deformation quantization of A nu as Poisson A module. So now you see we have to consider deformation quantization of modules. So to this end, let us recall the twisted Hochschild homology of a twisted algebra. So suppose sigma is automorphism of algebra A. Then you see we call this pair A comma sigma twisted algebra. Now equip A with a new called twisted A bimodule structure as follows. So the underlying space is A itself, but with a product with the A bimodule structure like this. So if you multiply mu to x from the left-hand side, is the same. But from right-hand side, you first have to apply the automorphism sigma to V and then apply to it. So it's easy to see this is again A bimodule. This is called a twisted A bimodule. We have the following. So suppose A is in Dorgochev's theorem. So then the deformation quantization of A nu is exactly, you see, this deformation quantization of A, but with this twisted module structure, bimodule structure. So now let's combine the result of this theorem with Kontsevich's and Dorgochev's result. Together with Poincare duality, we have the following theorem. So suppose R is the polynomial algebra, then we have the following isomorphism, community diagram of isomorphisms. So the horizontal maps, the upper one is given by Poincare duality for Poisson algebras. And you see this is called non-commutative Poincare duality for associative algebras, the second horizontal line, which is due to Vandenberg in 1998. And the vertical line here, the left vertical line is given by deformation quantization. And then this one is also deformation quantization. So here, this A nu is, its quantization is AH twisted with sigma. So this is isomorphism of commutative diagrams. So now you see, we said we have BV and so on the Poisson cohomologies. Actually, we have the following result. You see, suppose now A is a Poisson algebra with a semi-simple modular vector. Then you see Poisson cohomology and Hochschild cohomology of its quantization are isomorphic as BV algebras, and their negative cyclic homologies are isomorphic as gravity algebras. But I have to remark that the BV algebra for associative algebras with semi-similar Nakayama automorphism was previously obtained by Kovacic and Kramer in the paper published in Creos. So the gravity algebra was obtained by myself and Eshmatov and Liu. So now you see, as shown by Cattaneo and his collaborators, Kontsevich's deformation quantization also holds for graded Poisson algebras. So now you see, by the same argument as Dorgochev, and the deformation quantization of this exterior algebra, which means it is a finite dimensional Poisson algebra with a pairing. And then its deformation quantization is not necessarily to be commutative. So it's just a Frobenius algebra. And then we have the following theorem. Suppose H is a Frobenius Poisson algebra, then the following diagram commutes. All the morphisms are isomorphisms. And we can get the BV and so on its Poisson cohomology and BV isomorphism and gravity isomorphism like before, which I will not say much. The last part of my talk is, you see, we have another duality, which is given by called Kouzou duality. So I will start just from example. Now suppose A is a polynomial algebra with a quadratic bivector like this. And then you see its Kouzou dual denoted by A shrek is exactly the graded symmetric algebra as we studied in Kouzou duality for algebras. So you see, let's consider the dual bivector. You see, this is now, you see, I have a correspondence here, partial over partial xj. It corresponds to the xi j. And this xi is corresponds to this partial over partial xi. And then the others, other coefficients remain the same. Then you see under the correspondence, like what I said just now, we have the following as a observation, which is due to Shochet. It says that if pi is Poisson, then you see pi shrek is Poisson. The reverse is also true. If pi shrek is Poisson, then pi is Poisson. So we say that A shrek, pi shrek is a Kouzou dual Poisson algebra of this A pi. So now you see we have the following. Suppose A pi and A shrek, pi shrek are the quadratic Poisson algebra Kouzou dual to each other. Then we have an isomorphism between Poisson cohomology of A and Poisson cohomology of A shrek. And Poisson homology of A with, well, now it's not Poisson homology, it's a Poisson cohomology of A shrek with value in its dual. So this is easy to prove. Just write down the complex, the corresponding complexes, then use this identification. Then everything is isomorphism as complexes. But you see, now we are more interested, as I said, we are more interested in this twisted version. So now you see the theorem is, suppose A is a quadratic Poisson algebra and let A shrek to be its Kouzou dual, denote by nu and nu A shrek to be the modular vectors of A and A shrek respectively. Then they are also dual to each other. In the following sense, if you apply this correspondence, then one becomes the other. So then you see we have the following commutative diagram of isomorphisms. So the horizontal ones are twisted polar duality, and the vertical ones are Kouzou duality. So now you see Shochet and later Kalak and his collaborators show that the conservative deformation quantization preserves Kouzou duality, which means for a quadratic Poisson polynomial algebra A, if we denote their deformation quantizations to be AH and A shrek H respectively, then they are Kouzou dual as associative algebras. So now if we take the modular vectors into account, we have the following diagram. So following theorem, suppose A, H, and A anti-shrek H bar be Kouzou dual Poisson algebras. Then we have the following commutative diagram of isomorphism. So here, the left-hand side is like before. So the horizontal one is given by Kouzou duality, and the vertical ones are given by deformation quantization. And here, it's the same. You see, this is deformation quantization. Here, this is also deformation quantization. So now it relates. The point of the second diagram is, you see, it relates the twisted polar duality or twisted Poisson cohomology with a twisted partial cohomology of its quantization. So But I have to say that you see the causal duality between preserves Hausdorff cohomology was obtained by Taylor. So now combining the previous results, we have the following cube. So let A H and A shrek H be causal dual Poisson algebras. Then you see we have the following diagram of isomorphisms. It's a little bit complicated. So the top square are Poisson homologies in various sense, and the bottom are the say Hausdorff homology or cohomology in appropriate sense. So this cube commutes. Here, the horizontal arrows are given by Poincaré duality, and the vertical arrows are given by deformation quantization, and the slanted arrows are given by causal duality. So this is a commutative diagram of isomorphisms. So now you see as an application to this theorem, we have the following result. Assume that the modular vector of A is semi-simple. Then we have the following result. You see, here we have this is a commutative diagram of isomorphisms of BV algebras. As I said, if the modular vector of A is semi-simple, then this one, Poisson cohomology, has a BV. And then the Poisson cohomology of this Frobenius Poisson also have a BV. So they're related by causal duality. And then this one is given the vertical line given by deformation quantization. And then this also gives by deformation quantization. And this one is given by causal duality again. This is causal duality in the sense of associative algebras. So they are isomorphic as B. And you see, if you take cyclic homology, then we have the following. You see the negative cyclic homology of A and the cyclic cohomology of A shrek. Here, I mean in the Poisson sense. And the negative cyclic homology of its quantization is this is a cyclic homology of associative algebras. And this is the cyclic cohomology of its quantization of the quantization of A shrek. So it's also a cyclic homology of associative algebras. So they are also isomorphic as gravity algebras if the module vector is semi-simple. So I stop here. Thank you.
Thank you. Thank you. I actually didn't see the example come up, but before that.
I said that you see the example is given is here. It's very sketchy. So to get a semi-simple one, you just consider the sigma of say this xi1, xi2 partial over partial xi1 wedge partial over partial xi2. So here if I equals j, then this is a semi-simple quadratic bivector. This is what I mean by example.
I see. Yeah. Are examples all like this, or that are there other examples?
I mean, yes. Actually, you see, there is a book called Poisson Structures. There is a special, there is one section which especially discusses this semi-simple Poisson vectors. They have more examples, but I don't have the book now.
Okay, no problem. So I see Dima has another question. Dima, do you want to go for?
Hi. Thank you.
Hi.
Yeah, so I just want to make sure that I understand this semi-simplicity condition. So does that mean that you're having the modular vector field act on differential forms? And that action, just by the Lie derivative, and that action is semi-simple?
No, you see, on different forms, you see, I mean, I sum over all the eigen, no, it's not sum. You see, I consider, I say, how to say, let me go to, here, right? So I mean, this one, you see, nu is diagonalizable, and then you see if you consider say for example here, consider suppose this is diagonalizable, then you see you will have several. You can decompose this Fi to be eigenvectors, right? It may not necessarily to be just the same eigenvalue, but if you consider the sum of all this, then you see this is what I mean by eigenspace here. Is it clear?
So it's that operator mu tilde acting on differential forms that is and that action is diagonalizable.
Yes, yes.
Okay. Okay. Thank you. So may I ask another question?
Yes, yes.
Yes. So another question is, do those BV and gravity algebra structures lift to the chain level?
Oh, you mean, is it true on the chain level?
Well, on the chain level, I guess you would. What the question is, for instance, for the BV case, do these Lishnerovich co-chains, or sorry,
Yeah.
I'm sorry, the Kozyl-Brzezinski chains, do they have an action of chains on the framed little disk operator? So that's one for which the cohomology is the BV.
Yeah, this is a hard question, right?
I know it's a provocative question, but I mean, have you thought of?
You are right, but you see, a hint probably is like this. If you consider, for example, the deformation quantization, right? Then it's a deformation quantization is algebra over the little disk operator, right? And probably you are right. Infinitesimally, still it is true, but I don't know the proof. But this is a good question. Probably I have to think about it.
Okay, thank you. May I ask one last question?
Sure, no problem.
About the Kozyl duality, because it seems that would work in for polynomial superalgebras. Like when you have several even and several odd generators with a quadratic even or odd Poisson structure.
Yes.
You could do this whole thing more generally, probably.
Yeah, you are right. This is also a good question. Actually, you see, as I said, you see here, I can say R to be the functions on supermanifold, say R n0, and the exterior algebra is functions on the supermanifold R0n, right? So you see, this holds in general between R m n and R n m, right? So still that is true. I just didn't mention it. So you are right. It holds in a more general setting. It's not necessary to be just like this. This is probably called Poisson fermion correspondence or something like that, right?
So does this statement then hold for both even and odd Poisson structures on
yes,
superspaces?
I think so. Yes, you are right.
Very nice. Thank you.
No problem.
Great.
I have a question.
Yes.
A gravity is a gravity algebra an infinity algebra?
Yeah, you see, you are right. You see, let's go to the definition. It is a Lie algebra with more brackets, which are called the higher brackets. You see, let's go to the definition. If you have say there is no y, okay, no y. If you have three terms x1, x2, x3, then this is exactly the Jacobi identity. So you see, a gravity algebra, it consists a substructure called which is a Lie algebra. So it has more brackets.
Mm.
Yeah, I guess.
Don't worry. The diffusion quantization is interpreted as an infinity morphism.
Yes.
Also, yeah, can your theory is your theory interpreted as such a infinity morphism?
I don't know yet, because you see, I have a twisting, right? So I don't know, but if you transfer this area infinity, probably you are right. If you transfer this area infinity on the, say, polyvectors to the right-hand side, probably you are right. Probably you're right.
Thank you.
And no problem.
So what? There was a question from audience asking whether the gravity algebra is an L-infinity algebra.
No, it is not an area infinity algebra. So you see from here, you see area infinity algebra means you have higher operations, which are giving which gives the homotopy for Jacobi and homotopy of homotopy and so on. But here it's not. Actually, you see the Kuzu dual. Well, in the opera sense, it's like this. It gives the form of Frobenius manifold structure. Actually, this is proved again by Getzler. So it's not area infinity.
We cannot hear you.
Oh.
For 10 seconds or 5 seconds, we cannot hear.
Oh.
Sometimes you accidentally block the microphone and the volume disappears. It was rare, but it did happen.
Okay, is it better now?
Yes, right now it's perfect.
Okay, so just now I said it is not the area infinity algebra, because you see area infinity algebra is a bracket together with higher operations called homotopy for the Jacobi identity and so on, right? But here it's not. These brackets are not the homotopy for the bracket and so on. For homotopy for the Jacobi identity and so on. So it's it's a Lie version of this called form of Frobenius manifold structure.
Okay, so if there is no more question, let us thank the speaker again.
Thank you for inviting.
For the talk. And, so see each other next Thursday.
Thank you. Bye bye.